Welcome to Aeon Timeless History, where the past meets power, and the smallest things hide the greatest secrets. Imagine this: a tiny object, no bigger than a peanut, sitting silently in the palm of your hand. It doesn't glow, it doesn't move, it doesn't look dangerous, but inside, it holds enough energy to power an entire city. Not for minutes, not for days, but for months, even years. This is the story of uranium, a material pulled from deep within the Earth, transformed by human intelligence, and capable of both creation and destruction on a scale humanity still struggles to fully comprehend. Today, we are going deeper than ever before, from ancient rock formations to the birth of nuclear science, from secret wartime laboratories to the massive reactors powering modern civilization. And by the end of this journey, you will never look at energy the same way again. Before we begin, if you're fascinated by hidden histories, untold science, and powerful stories like this, make sure to subscribe to Aeon Timeless History, and tell me in the comments, would you trust nuclear energy to power your future? Let's begin. The story of uranium doesn't begin with power plants or bombs. It begins in 1789. A German chemist named Martin Heinrich Klaproth was studying a strange mineral, a dark, heavy rock known as pitchblende. He isolated a new element and named it uranium, after the planet Uranus, which had been discovered just 8 years earlier. At the time, it meant nothing. No one knew what it could do. No one imagined its power. For decades, uranium sat quietly in laboratories, used mostly for coloring glass and ceramics. It was just another element. Until 1896. A French physicist named Henri Becquerel made an accidental discovery. While studying uranium salts, he noticed something strange. Even without sunlight, the material emitted invisible rays, powerful enough to expose photographic plates. This was the moment humanity discovered radioactivity, and everything changed. Soon after, Marie Curie and Pierre Curie took this discovery further. They uncovered new elements, radium, polonium, and revealed something shocking. Atoms were not stable. They could break apart and release energy. A completely new understanding of physics had begun. But no one yet realized just how much energy was hiding inside. Fast forward to 1932. A British scientist named James Chadwick discovers the neutron. This tiny, neutral particle would become the key to unlocking the atom itself. Because unlike charged particles, neutrons could slip directly into the nucleus. And when they did, something extraordinary could happen. In 1938, two German scientists, Otto Hahn and Fritz Strassmann, conducted an experiment on uranium. They bombarded uranium atoms with neutrons, and what they observed was something no one expected. The uranium atom didn't just absorb the neutron, it split in half. This process was called nuclear fission, and when it happened, it released an enormous amount of energy. But even more important, it released more neutrons, which could go on to split more atoms, creating a chain reaction, a self-sustaining explosion of energy. For the first time in history, humanity had discovered a way to unlock the energy of the atom, and that power would soon be used in ways the world would never forget. World War II. The stakes were global, and scientists feared one terrifying possibility: that Nazi Germany might develop an atomic weapon first. So the United States launched one of the most secretive scientific programs ever created, the Manhattan Project. Led by brilliant minds like J. Robert Oppenheimer and Enrico Fermi, thousands of scientists worked in complete secrecy. Their mission: turn uranium into a weapon. But there was a problem. Natural uranium is mostly made of uranium-238, which does not easily undergo fission. The rare isotope, uranium-235, is the one capable of sustaining a chain reaction. But it makes up only 0.7% of natural uranium, So they had to find a way to separate it. This process became known as enrichment. Using massive facilities, they developed techniques like gaseous diffusion, electromagnetic separation, and early centrifuge systems, all designed to isolate uranium-235. After years of work, they succeeded. And in August 1945, the world saw the result. The atomic bomb dropped on Hiroshima, powered by enriched uranium. In a single moment, the world entered the nuclear age. After the war, the question became, can this power be used for something else? Not destruction, but energy. The answer was yes. In nuclear power plants, uranium is enriched only to 3 to 5%, just enough to sustain a controlled reaction, not an explosion. Inside a reactor, atoms split slowly, releasing heat. That heat boils water, creates steam, and spins turbines, generating electricity. Today, nuclear energy provides around 10% of the world's electricity. Clean, powerful, and efficient. But to understand how this works, we need to go deeper, much deeper, into the Earth itself. Uranium doesn't come from factories, it comes from the Earth, hidden in rock formations, formed over millions of years. Countries like Kazakhstan, Canada, Australia produce the majority of the world's uranium. But one location stands above the rest: Saskatchewan, Canada, home to the highest grade uranium deposits on Earth. Here, uranium concentrations can exceed 20%. That's up to 100 times richer than typical deposits. But extracting it is incredibly dangerous. Above the ore lies a layer of rock filled with groundwater. If disturbed, the entire mine could flood. So engineers developed an extreme solution: artificial ground freezing. They drill hundreds of holes, insert pipes filled with freezing liquid, and lower temperatures to -22 degrees Fahrenheit. This freezes the water, creating a solid barrier, allowing safe extraction. It's like turning the Earth into ice, just to reach the uranium below. Once mined, the uranium ore is crushed, ground into fine particles, and mixed with water. Then, it undergoes chemical processing. Acids dissolve the uranium, separating it from other materials. The result? A concentrated substance known as yellow cake. But it's not ready yet. Next, it's converted into a gas, uranium hexafluoride. This gas is fed into high-speed centrifuges, spinning at incredible speeds. Because uranium-235 is slightly lighter, it separates from uranium-238. Step by step, the concentration increases until the desired level is reached. This is enrichment, the heart of nuclear technology. Now comes the transformation. The enriched uranium is turned into uranium dioxide powder, then compressed, under extreme pressure, into small cylindrical pellets, each one about the size of a peanut. But inside, incredible energy. One pellet equals 1,800 pounds of coal, or 150 gallons of oil. Let that sink in. This tiny object replaces entire truckloads of fuel. The pellets are then heated, hardened, and placed inside zirconium tubes. These become fuel rods. Dozens of rods are assembled together, forming a fuel assembly, ready for the reactor. Inside a nuclear reactor, everything is controlled. Precision matters. Neutrons strike uranium-235 atoms, splitting them. This releases heat, more neutrons. The chain reaction continues, but is carefully regulated. Control rods absorb excess neutrons, preventing runaway reactions. The heat turns water into steam, which spins turbines, generating electricity for millions of homes. All of this from atoms splitting apart. But there's a cost. After about a year, fuel becomes spent, still radioactive, still dangerous. These fuel rods are placed in deep cooling pools, where they remain for decades. Worldwide, hundreds of thousands of spent fuel rods sit underwater.
silent, but powerful. Managing this waste remains one of the biggest challenges of nuclear energy. Today, the world faces a critical question. How do we power the future? Fossil fuels are running out. Climate change is accelerating. Renewable energy is growing, but not always reliable. Nuclear energy offers a solution: low emissions, high efficiency, massive output. But concerns remain: safety, waste, cost. New technologies like small modular reactors and fusion research may redefine the future. But one thing is certain: uranium will continue to shape the world. Now I want to hear from you. Do you think nuclear energy is the future, or is it too dangerous to trust? Drop your thoughts in the comments. From a forgotten element in a laboratory to a force that powers nations and changed the course of history forever, uranium is more than just a material. It's a reminder that the smallest things can hold the greatest power. This is Eon Timeless History.